The vacuum speed of light is invariant, or unchanging, in all reference frames. That is, if you turn on your flashlight in a vacuum such as space, you would measure the light to be moving at the vacuum speed of light, which we call c, equal to 299,792,458 meters per second relative to u. If Peck flew by on a rocket and measured the same light from your flashlight, he would measure the light to be moving at the same speed relative to him. This holds true no matter how fast Peck is moving relative to you. Even if he moves at 90% the speed of light, he would still find that the light from your flashlight is traveling at the exact same 299,792,458 meters per second. This may seem more like science fiction than reality. After all, this is not how relative velocities work in everyday life. But numerous experiments have confirmed that the vacuum speed of light is indeed unchanging. In fact, this fact is one of the two fundamental postulates of Albert Einstein's special theory of relativity, with the other being that the laws of physics work the same way in all inertial, non-accelerating reference frames. This invariant speed has many intriguing implications, one of which is that time flows differently for observers moving at different speeds. To see this, say you're in space again with your trusty light clock, which uses a photon bouncing off two opposing mirrors to measure time. Say in some time delta tau, the clock ticks once as the photon moves one half cycle. We can then determine that the length of the clock must be the speed of light times delta tau. Suddenly, Peck flies by on his rocket, moving at a velocity v relative to u, with an identical light clock. From your perspective, the photon in his light clock follows a longer diagonal path at the same speed of light. If we let Peck's clock tick with interval delta t, we can draw a right triangle with the diagonal distance of his photon, c delta t, as the hypotenuse, and the length of the clock as one leg. The other leg then becomes the distance Peck travels in a tick of his clock, v delta t. Using the Pythagorean theorem and rearranging, we find that delta t equals delta tau over the square root of 1 minus v squared over c squared. This means that Peck's clock ticks slower than yours, so you observe time passing more slowly for objects moving relative to you. This time gets slower the faster that object moves. This effect is appropriately called time dilation. Now say Peck travels from where you are to a stationary planet in one tick of his clock. You can calculate the distance he travels, which we call L0, by just multiplying his velocity by the time it takes for his clock to tick once and getting v delta t. In Peck's perspective, he is still moving away from you at velocity v, but one tick of his clock in his perspective is a time interval delta tau. Thus, from his perspective, the distance he travels, which we can call L, is given by v delta tau. Using the time dilation expression we discovered earlier, we see that these quantities can be related by L equals L0 times the square root of 1 minus v squared over c squared. This means that an observer moving relative to two objects measures the distance between them as shorter than a stationary observer, an effect we call length contraction. Of course, Einstein also said that physics works the same in all inertial frames of reference, so all of this goes both ways. For instance, even though you measure Peck's time as moving slower than yours, Peck measures your time as moving slower than his, due to your velocity relative to him. And if you both hold identical rulers, each of you will think that the other's ruler is shorter. Neither of you are more right or wrong than the other. You just have different perspectives.